Okay, so the last two topics I got to talk about, well, it's really just one topic. I want to talk about inequalities. I'm going to start at like the very beginning because, like Mary Poppins said, it's a very good place to start. Is that Mary Poppins? Who sang that song? You guys know the song I'm talking about? Let's start at the very beginning. It's a very good place to start. No, it's Sound of Music. That's what it is, Sound of Music. Anyways. Watch the Sound of Music if you haven't, if you don't get that reference. I just want to start at the beginning in case you guys know literally nothing about inequalities. So I apologize if the first few slides are like, I don't know, boring because you get this, but these are the 4 inequality signs that I'm hoping you've seen before. It's the little like, I don't know, maybe you learned about them as like crocodiles or alligators that eat the other side. You ever get taught how that works? Okay, maybe I can speed this up then. You could write a statement that says that 2 is less than 4, if that's a true statement. Or -3 is actually greater than -4. You gotta think about that one for a second, because on a number line, like here's -4 and here's -3. So -3 is on the bigger side of that. You guys are familiar with this? Okay. So our challenge now is to deal with inequalities as equations, though. So rather than doing it just with numbers, we're now going to deal with this as like x is greater than 2 or y is less than like this quadratic thing. That's our new challenge. I'm just going to talk a bit about the concept of solutions. Whenever you have an equation, equations are meant to be solved, and you're solving for, like, say, x. How many solutions can a quadratic have? Up to. How many possible solutions can a quadratic have? As many as? 2. It could only have one solution, and then there is that, I've said this before, if you guys learn anything from grade 11 math, I hope you learn this, is that the answer, there is no answer, is actually an answer now. Does that make sense? So, what makes inequalities challenging then is that there are so many solutions that everything could be an answer almost. Like, let me give you an example. X is greater than 0. Here's a list of numbers that you could have for your solution. 1 is greater than 0. 2 is greater than 0. 3 is greater than 0. 900 is greater than 0. But like then you can do decimal numbers. 1.1, 1.2, 1.3. Does that make sense? The problem we have here then is that there are not just one answer or 2 answers or 3 answers. There are an infinite number of answers that are greater than 0. So the way it changes is rather than having a solution, you have a solution set. And basically this just refers to all of the possible answers because there are so many you can't even count them all. Does that make sense? Because you could do all of the whole numbers. You could use all of the decimal numbers. You could use all of the decimal numbers that have 2 decimal places, all of the decimals that have 3 decimal places. Right? Like you can never count all of these. Okay. Usually what we do then is because there's not a finite. Do you guys know that word finite? No. Okay, what's the opposite of finite? It would be infinite. Infinite means that there's like it goes on for forever. So since there's not a finite number of solutions, so because this goes to infinity, we either have to represent this either visually in some sort of way. And so the 2 most common ways of representing this is a number line or a solution region. You guys, I'm guessing, have seen number lines before. But if not, let me just review how this works. Let's say I told you that x is less than or equal to 0. The way that we visually try to represent this is we draw out like a line and we put a whole bunch of little notches on here for all the, usually the whole numbers and integers. And then if it has to be less than or equal to 0, we kind of draw like a line going one way saying, look, all of the answers on this side of 0 over here, you can use anything on that side. Does that make sense? Have you guys done this before? Okay. Do you guys know the difference between how to deal with the one with the bar underneath and the one that doesn't have the bar? Do you know how to? Yeah, basically that's it. This bubble right here is filled in. This one right here, I know you can't see it, but it's supposed to be like open. This one right here is also open because you don't get to include one, but this one right here is filled in because you do get to include one. Does that make sense? Cool, moving on. Our goal then might be to try to solve an inequality like this. So I'm guessing you probably haven't done this before. Okay, so here's how you'd solve something like this. Pretend there's no inequality, just pretend it's an equal sign. So hypothetically, if it was an equality, it would look like this. How do you solve it if there's an equal sign? Sure, bring x to one side, so I'll bring the 2x to the other side, minus 2x. So you'll have x plus 4 equals minus 1. Okay, here's what I've proven. X equals minus 1. Okay, but that's actually not at all true.
Amen.
Because what ends up happening here is that it's either bigger than minus 5 or smaller than minus 5. So we want to represent this using like a number line. So what I like to suggest is draw out a bit of a number line. I'm just going to put minus 5 there. Minus 4, minus 3, minus 6, minus 7. That's good enough. There are some rules for working with inequalities that you may have learned. One of them is like if you ever divide by a negative number, you have to flip the inequality sign. You ever heard that before? Even if you haven't, I don't care because I don't like teaching that way. I like to teach to solve this, use a test point. I think this is the most effective way of solving things. Minus 5 is a very key point right here. I'm going to keep it with an open-faced circle. And the reason I'm going to make it open-faced is that this little inequality we started with there doesn't have the bar underneath. Does that make sense? It means that I'm either going to be shading that side of the line or this side, one of the two. And to solve that, I'm just going to pick a random point and test to see whether it should be that side or not. So I'm going to pick a test point over here. Give me an example of a number that's bigger than minus 5. Minus 2 would work. 0 is probably the best choice, though. I'm going to plug in 0 right here. 3 times 0 plus 4, what does that equal? 4. 2 times 0 minus 1 is minus 1. Is 4 less than minus 1? Okay, it is not. So that means this is not where my answers are, so I should not be shading there. Just to confirm them, let's pick a number on this side of the line and see what happens if I pick a number that is less than minus 5. So like say minus 10. 3 times minus 10 plus 4. That would give minus 26. 2 times minus 10 minus 1 would give minus 21. Is minus 26 less than minus 21? Yes. So that means that this is not where we should have answers. And this side over here is where we should have answers. So now just draw like an arrow. I like to draw it like this myself. Just indicating that my solution set is everything on that side of minus 5. So minus 6, minus 7, minus 8, minus a million, minus 2 million, minus 5.2, minus 5.3. All of those are answers. So we try to draw it visually as a way of representing our answers. Does that make sense? Let's try another one. Determine this solution set. Okay, well, again, it's got an inequality. Ignore the inequality, just make it an equality. So just pretend there's an equal sign there and solve like you normally would. X squared minus 2x now equals 3x plus 6. What kind of equation is it? Okay, so how many solutions could a quadratic have? I don't know that it has to, but at least it could have to, right? So to solve a quadratic, make everything equal to 0 in either factor or quadratic formula. So I'm going to bring everything this way. X squared minus 5x minus 6 equals 0. This is really similar to the one that caught you guys last day when Forrester was here. How do you factor that thing? Add to minus 5 times to minus 6. Jimmy, you said 1 and negative 6. That'll do. Good job. Does that make sense so far?
Yeah.
So I've got x plus 1, x minus 6. So I've got points at negative 1 and positive 6. Those, if you take math further on and you get to like calculus, we call those critical points. I don't think that really matters for our class at this point yet, but these are called the critical points. I'm going to plot them on a number line then. So unfortunately, this one's a little bit wider, so I'm going to have to actually plot almost all these points. Let's see, 6, 5, 4, 3, 2, 1, 0, negative 1, negative 2, negative 3. That should do. Maybe I'll go one further and go 7. All right, first question you have to ask then is, are we allowed to include negative 1 and 6? Is it an equals greater than sign or a greater than and equal to sign that we started with? This sign right here is just a like less than sign, so we don't get to include negative 1 and 6. So I'm going to draw an open circle on negative 1 and on 6. Well, there's a couple possibilities. What could happen is there could be answers over here. There could be answers in between here. And there could be answers over here. And our goal then is to test and figure out in all of these sections where answers could possibly be. So let me try a test point. Let's try a test point that would be in this region over here. We need some number that is clearly less than minus 1. Sure, negative 3 will work. So go back to the original. Negative 3 squared would give you 9. And then you'd have to subtract 2 times negative 3. So you'd have like a couple of negatives there. So you'd actually be adding 6. So I believe this side here would be 15. Then over on this side, we're plugging in negative 3. So 3 times negative 3 will give you negative 9. And when you add 6, that'll give you minus 3. Is 15 less than minus 3? It is not. So I should not expect to have any sort of answers in this section of the graph. Now pick a number that's somewhere between negative 1 and 6. 4 works. I prefer 0 myself. You can do 4 if you want, though, but I'm going to do it for 0. That's 0. That's 0. That's 0. That's 6. Is 0 less than 6? It is. In theory, then, every number in this region of graph should work. So you could try the rest of them if you want, but this is the whole point behind a solution set. Do you really want to also test 1, and then test 2, and then test 4, and then test 5.3, and then test, you know what I mean? In theory, every number in this region of graph should work if you did it right. So what I'm going to do is I'm going to draw like a little bit of a bar between these ones then. I don't get to draw an arrow, unfortunately, because it doesn't extend for forever, but this is a visual way of representing that every answer in this region of graph here should work. Usually what ends up happening is either the outside sections work or the inside section works, but we should just confirm just to make sure. So pick a number greater than 6. Right? Sure. 10, 7, I don't care. 10? If this is 10, that's 100. But then you're minusing 20, so that side's 80. And then if this side over here is 10, it's 30 plus 6, so it'd be 36. Is 80 less than 36? No, it's not. Which is good, because I wasn't expecting answers there either. So I'd say there's not answers over here, but there are answers in this region of graph. Does that make sense? Visually, the way a quadratic works is like a quadratic works like, say, something like this. If I were to ask you where this quadratic was less than 0, you would say the quadratic is less than 0 in this little section here. And it's almost like you could look at it as here's where it starts and here's where it finishes. and everywhere in this little section, it's less than 0. If I were to ask you where it's greater than 0, then the possibilities would be, well, starting here, everything that way is greater than 0, or everything that way is greater than 0. So usually the way a quadratic works is you plot 2 points on a number line, and either you have the answer in between, or what ends up happening is the answer is the outside edges, each going outward like this.
So if it's the outside edges, would it be like for this other one, would it have been everything less than -1 and everything more than -6, or would it just be one side?
No, usually what ends up happening is it ends up being, if it's not in the middle, like it was for our example, then it's everything less than this number, but bigger than this number. It is also possible, by the way, for the solution to be everything or nothing. Okay, let me show you an example here. Let's try to figure out the solution set for where x squared plus 4 is greater than 0. Now, we could do what we were doing before where we try to solve this quadratic. There's a problem with trying to solve this quadratic. I'll show you in a second here. X squared plus 4, let's say it's equal to 0. How do I solve that? Well, it's actually not a difference of squares because it would have to be x squared minus 4. So it's not a bad thought. It doesn't work here. What you could do is you could make it x squared equals -4 and then try to square root. Can you square root? It's not possible. So it might be better just to look at what this graph looks like. What does x squared plus 4 look like as a graph? What does an x squared graph look like? It's a parabola. Should probably look something like this by the time you're done. It'll be x squared, that plus 4, move the vertex up 4. Where is this graph bigger than 0? For the y values, by the way. Where is the y value of this graph greater than 0? Everywhere. Does that make sense? There is no point to plot on the graph because literally, like, x is everything. Every single x value you plug in will make this greater than 0. If you plug in 0, you'll get a positive number. If you plug in 5, you'll get a positive number. Does that make sense? So if I had to draw the solution set, this would look kind of weird, but it would literally be a line that goes in both directions for forever.
Mr. Patton, please dial 103. Mr. Patton.
Does that make sense? Mathematicians developed a faster way of doing this. You guys have already learned this at some point. Sometimes we say this. X is an element of the reals. It's kind of a faster way of saying, look, every single number is valid. Let's try the second one here.
Sheridan George, please come down to the office. Sheridan George.
Let's say that I asked you where x plus 3 is less than 0, but it's absolute valued. What does absolute value mean to do? Well, let's just put it this way, we'll make it positive. Right? An absolute value graph should always be positive. How do you take an absolute value graph that's always positive and have it less than 0? Is that even possible? So then if I had to draw up the number line, it might look like this. You'd have like your number line, and you'd have nothing there. Or like, there is no value of x that you can plug in that will make this less than 0. You can even try some. If you plug in 1 plus 3 would be 4. 4 is not less than 0. You might try -7. -7 plus 3 would be -4. But then you have to make it +4. And so, do you guys get what I'm saying here? Literally, there is no way for this to work. So if you draw the empty number line, that would work. The other way we often write it is like this. X is an element, and then this is a fancy notation you probably haven't seen before, of a 0 with a line through it. Have you seen that before? I'm doubting, because I don't know why you would have. This is referred to as the empty set. Basically, it's a fancy way of saying that fx is nothing. Now, the way we're phrasing this, though, is that x is not 0. Because if x was 0, that would actually be something. What I'm trying to tell you here is, like, there are no answers. So this is like a fancy way of writing that, like no answers. I didn't draw those brackets in the way they're supposed to. Do you guys know the brackets I'm talking about though, where it goes like this, like that fancy bracket? I suck at drawing them. Have you seen those before? Where it's like a parentheses. Is that the right word to use? You put like a 0 through it and a parentheses. Anyways, that's the fancy shorthand notation of literally saying there is no possible value for x. I'm not saying x is 0. I'm just saying there's no answer. Does that work? Cool. All right. I'm thinking so far some of this you knew and some of this you probably was a little bit new, but nothing there is like a really huge leap yet. All right, now let's make this a big leap. How do we solve this? Okay, well, we just talked through the steps. What do you do if you get an inequality sign? Pretend it's an equal sign. Pretend it's an equal sign. So now what we have is x bracket x minus 2 equals 4x plus 3 minus 3x, 2x minus 1. I know it's not actually equivalent, but what we're looking to do right now is just solve for some points to plot on a number line. So solve. We learned how to do this at the beginning of our school year. How do we solve something like this? Foil it, yeah. Untangle the knot. This is a mess, so let's foil the crap out of this thing. You got x squared minus 2x over here. 4x plus 3 minus 6x plus 3x. That it is. Thank you. Good catch. Good job. All right. Now what do I do? Yeah, combine all the, well, bring everything to one side and combine like terms kind of goes together, I guess. So my personal preference is always to make the x squared term not be negative. So you can go the other way, but I'm going to bring everything this way. So you'd have 7x squareds. Let's see, that'd be minus 6, minus 3 more, minus 9x? Minus 3. That's what I got. So you're minusing 4 and you're minusing 3. 9. Adding the 6 gives 7. Yeah. Any issues with that? In theory, you could try factoring this. Boy, that's gross. You need things that times to give 21 because of the 3 and the 7 up front, and not a lot of stuff actually multiplies to give 21. Because you need either 3s and 7s, but that doesn't have to give 9, or 1s and 21s. So then how do we solve it? Yeah, quadratic formula. It's a useful formula. Okay, I need a calculator for part of it. 9 squared is 81. 4, 7, and 3 gives 84. Double negative means you're adding them. So we root 165. I got that. 9 plus or minus 165 square rooted over 14. Okay, depending on what kind of unit you're working on, you can either leave it at that answer there, because that's actually a valid place to stop. Or if you want to, so you have a sense of what this number looks like, we could find its positive and negatives as decimal numbers. I think this would be an appropriate time to actually find those values. 9 plus the root of 165 divided by 14 is about 1.56, give or take. And negative 0.27. Anybody get anything different than that? Okay. Now what do I do? This wasn't actually an equality, it was an inequality. So what do we do with inequalities recently? Yeah, plot it on a number line. I don't need to make the number line massive or anything here. Okay, here's the only difference is these aren't whole numbers. So like what I might do is go -2, -1, 0, 1, 2, 3. And I'm just going to kind of put in a new little line for where these ugly irrational numbers go. So like 1.56 is going to go roughly right about there, I guess. Just going to write a little note. That's a 1.56 or so. And negative 0.27 is going to go right about here, I guess. Do I get to include those values or no?
Yes.
Okay, so if I do get to include them, then closed faced circle. And then what I'm expecting to have happen is either the section in between is where we have answers, or the outer sections are where we're going to find answers. One of the two. So let's try some test points. Something lower than this.
-1.
Sure, -1 will work. We just got to go way back up to the very top. You should always go back to the very original equation. So I'm plugging in -1 everywhere. This kind of stinks though. -1, and then we have -1 minus 2. That's from -3. And when you change that, this should be a 3, I believe, when you're done. For the other stuff, why don't we use a calculator? I mean, not that it can't be done by hand, but this is why they invented them. You just gotta make sure you get all those brackets right. I got -10 myself. Check your brackets, see whether you have as many closed brackets as you have open brackets. That's probably the reason why you get an error.
I got 5.
Okay. Anybody else try it?
-22.
Okay. Alright, maybe I should try it on the big calculator just to try this here. I'm going to do 4 bracket -1
Oh.
plus 3 minus 3, and then directly next to it I need a -1. Then I need another bracket for the 2. Then I need a bracket for -1. Then -1. And then I need one more bracket.
Oh, that's how I got -10. Oh, oh, wait. Because the first time I did like the whole negative sign, not the subtract.
Oh.
I got -10. Oh, yeah, I got the negative sign.
Rather than the 2 different negative signs you have backwards? No. Long story short, is 3 greater than -10? Yes, it is. Kind of think about that for a second, but 3 is way over here, -10 way over here. So that means that the test point we tested was -1. I believe it should mean everything in this vicinity and further should work. At this point here, if you wanted to, you could probably just make the assumption. It's a bad word to use, though. You probably know the acronym about assumptions, but you can probably assume that this is correct in this course. I would not do that past this course because there are exceptions to this. But basically, it's either going to be the middle section or it'll be the outside sections. So at least for our course, you can probably do it like this, but after this class, don't ever do that. Test every single section just to make sure. Does that make sense? Awesome. Okay. Honestly, that stuff that we just did is, I don't know, cool, I guess. But my goal now is to try to make it to a problem we can solve, because inequalities do have a use. Okay. Before we get to that, though, I want to talk more about the pictures of the graphs. Whenever we have an equation, did you want to move that out of the way, or?
No, it's good.
It's just like the sun is just shining on you?
Yeah.
All right. Whenever you have an equation with two variables, it really screws things up then. So far, like this equation I gave you right here, the only variable is x. What we have to do now is, what happens if I give you the equation y is less than or equal to x squared plus 4x plus 3? And it ends up changing things because depending on what x is, depends on how y fits. So I like to utilize a skill called reverse shading. And I've actually mentioned this to a lot of you guys in chem class before. The idea behind reverse shading is you shade where the answers are not. And so what ends up happening is all of the solution points are in the non-shaded section. So in this particular example right here, an xy pair that could work would be right here, 0, 0. Or 2 and 6. But you have to answer them as ordered pairs, as x's and y's. The way this changes is rather than you drawing like a number line, you're actually drawing a number line in an x direction and in a y direction, because you have to count for x and y. And then rather than shading just in one direction, we actually have to shade like as though it's a quadratic. So let me do an example. I think it's the best way of trying this. We're going to try to determine the solution set for this equation with two variables. We're going to do exactly what we just did, though. Pretend there's not an inequality. Pretend there's an equality. So pretend it's y equals 2x plus 1. Okay, well, you can't actually solve this in a way, but you can graph it. What does y equals 2x plus 1 graph into? Like, what is it going to look like? Yeah, straight line. I mean, use your calculator if you need to, but it should have a y-intercept of 1 and a slope of 2, so it should look something like this. Okay, so in a way, we're kind of drawing our number line. I should tell you the standard convention here. If this thing right here does not have the equals bit on it, standard convention is to draw a dashed line. So you draw it like this is how you'd sketch it. And that's kind of the way of indicating that you're not allowed to make it equal to. I'm sorry if you already drew that in and I didn't beat you to the punch. If there was a little bar underneath, then you would draw a regular line. Just so you know. So I'm just going to write that up here. Dashed line is for this or this. A solid line is the convention for those ones. So far, so good? Well, now it's exactly the same as the number line we just drew. Only rather than having a couple of points we're looking for, we're either going to shade all of one side of the graph or all of the other side of the graph. So what's going to either end up happening is we're going to shade over here or we're going to shade over here. So how do we figure out which side to shade? Use a test point. Pick a point that is clearly on one side of the graph or the other. So here, I'm going to pick this point right here. This point right here is clearly on one side of the graph or the other. What's its coordinates? I think it's 6 and 0. I don't care whether it's 6 or 7. It shouldn't matter though, right? Take those points and go back to your equation then. So plug in 0 for y. Plug in 6 or 7 or 5, whatever you have for there. Is 0 greater than, say, like 13? It's not. Okay. That means that this side of the graph is not correct. Okay. Here's where I like to flip this, though, because this actually has a purpose behind it. I like to use reverse shading. One of the reasons I like reverse shading is because often we'll have more than one equation. And so what's best to do here is if this is not where the answers are, then this side of the graph is all of the points that should work. So I'm going to shade where the answers aren't. So I'm going to shade this half of the graph. And what I've done here is I've visually made a picture that kind of lets you know that any point over on this side over here, any XY coordinate pair, should make this work. I mean, you could test one if you want, just to be confirming your work. Like, how about this one? This would be -10 with 10. This point should work. If I plug in 10, is 10 going to be greater than -19? Yeah. Does that make sense? Okay. I'm going to skip the next example then. I'm going to go back to the word problem. Okay, what we just did, I'm just trying to build background skills then so that we can actually use this to solve a problem. This is going to be typical of what I might give you on a test. So this is my goal, is we'll probably do this example here, and then I'll leave it up to you guys. We could do the next set of notes, which is just really more examples. Or if you want to, we can call it a day. I'll leave that up to you guys. Yeah, for sure. We'll do a break though. Yeah. Okay. But this is kind of our goal, is now that I've talked a bit about how inequalities work, let's use them to solve a question. So here's your scenario. There's a cake that requires 150 grams of flour, or a second cake that requires 75 grams of flour. Just to kind of like maybe differentiate them, why don't I call the first cake, let's say that it's chocolate. And sure, vanilla. So you might ask, why wouldn't you just make the one that requires less flour? But maybe people really like chocolate cakes, so you want to make a little bit of both. Okay. And here's the issue for the baker. The baker has a practical limit. Okay. There are a lot of real life scenarios where I have so much stuff, and once I use up my stuff, I can't make more. Does that make sense? And this is a limit here. The baker only has 2.25 kilograms of flour, or I should really change that. It's 2250 grams of flour. This is like your uppermost limit. So here's my first question. Let's try to define some variables in terms of x's and y's. Well, I might suggest that x could be how many chocolate cakes you make. And y could be how many vanillas you make. Because now I'm going to write an inequality. And I think I maybe should just write the first inequality for you guys. It's going to look like this. 150 x's plus 75 y's has to be less than or equal to 2250. Let's talk through this here. As a baker, you have 2250 grams. Do you have to use it all? I mean, you can. Can you use more than 2250 though? No. Like, practical purposes would say that that's your uppermost limit. So right here, this is how much flour it takes to make a chocolate cake. This is how much flour it takes to make a vanilla cake. And I don't know whether you're making 1 and 1 or 2 and 2 or 5 and 7, but however many of each type of cake you make, it better be less than 2250. Does that logic make sense? Now I'm going to graph this. Try to represent a solution set. How do I graph something like this, though? Okay, so first use an equal sign. So make it 150x plus 75y equals 2250. How do you throw that in your graphing calculator? What do you need to do in order to make it fit your graphing calculator parameters? Your graphing calculator needs you to get y1 and y2 and y3. It needs to get them by itself to fit in your graphing calculator. So we need to get y by itself, basically. How do you get y by itself? Subtract the 150, and then what did you say?
I just said bring x to 1.
Oh, okay, yeah, so same thing then. So make 75y equals 2250 minus 150x. And what else do I have to do? Okay, I'd like to give a hint on this one here. You could divide both of these terms by 75, but they may or may not actually divide nicely by 75. So one thing I like to do just to save time is I put all of this in brackets, and then I just divide by 75. Because like 150 is definitely going to divide by 75, but this 2250, maybe it does, maybe it doesn't. So when I type this in my graphing calculator, I'm going to type it in like this: y1 equals open bracket 2250 minus 150x divided by 75. Now I'm going to graph this thing. $22.50 minus 150x divided by 75. Okay, if you press your graph button, Lord knows what it's going to look like because it depends on what your window sizes are. So we should figure out what some reasonable window sizes are. What do X and Y stand for? How many cakes you make. I don't think you can make negative cakes. So you should probably start at 0. Reasonably, how many cakes could you make? 600? Let's go with 10 for now and we'll adjust from there. Again, for Y is now about how many vanilla cakes you make. Again, the least you can make is 0. You can't actually make negative cake, right? Again, maybe the most you can make is 10. Like, I don't know if this is enough for now, but we'll start with this. Okay, so apparently you can make more than 10 cakes. So let's expand it then. Go to 30. There we go, that's better. Alright, so if I want to graph this thing then, I just keep going here, my graph would look something like this. Bit of an axis. This goes from 0 to 30, from 0 to 30. That's a line that looks like this. And on one axis, this is about chocolate, and the other axis is about vanilla. I'm going to pick a point way out here. 25 and 27. Does the guy have enough stuff to make 25 chocolate cakes and 27 vanilla cakes? I doubt it. I think he's going to run out. But let's just confirm. If I go back to my inequality and I plug in 25 and 27, like I'm just making up random numbers here, is that number actually going to be less than 2250? Probably not. So would it make sense for me to suggest here that 25, 27, 25 of one cake and 25 of another cake is like too much? There's no possible way he can make that many cakes. He just doesn't have enough stuff. So therefore, if this is the side of the graph where things are not, the side of the graph where things do fit is this little triangle section right here. So what I'm going to do is I'm going to shade this section right here. Let me point out some points within this section here that are logical. Could, right here at 0, 0, could the baker make 0 chocolate and 0 vanilla cakes? In theory, he could. He could be a really lazy baker and make no money, obviously. But is that a valid thing for him to do? Sure, he has the stuff to make nothing. Here's a point. 2 and 10. Could he make 2 chocolate and 10 vanilla? Sure, he has enough stuff. Everything that's along this point right here would mean that he uses all of his stuff. So if I were to find a point along this graph, like for example, 3 and 24. 3 and 24 is a point right on the line. If he makes 3 chocolate and 24 vanilla, he uses every single gram of flour he has. That makes sense? If he were to make 9 and 12, 9 and 12 means, again, he uses every single gram of flour he has. Could he also make 8 and 12 and 7 and 12 and 6 and 12? Sure. Because all of the points in this little triangle right here are the number of cakes he could make where if he just doesn't use all of his stuff. Does that make sense? Okay. Last thought, then we'll take a break here. What's the meaning of the x and y intercepts then? Yeah. Right here, this x-intercept would be if he only ever made chocolate cakes. Let's say that he decides one day, screw it, I'm not making vanilla, I just don't want to. He just purely makes chocolate cake. Well, then how many chocolate cakes could he make? Looks like 15 based on this. So he could just make chocolate cakes and make 15 of them. Or if you looked for your y-intercept, that would be how many pure vanilla cakes he'd make. So he could just make 30 vanilla cakes. Or something in between. 2 and 10, 1 and 1, 0 and 0. Everything in this triangle right here is a possibility for the farm, or for the baker. The farmer's next. Does that make sense? Okay, last thought, then we'll take a break here. What we're going to do on the part 2 examples then, if you guys are feeling up to going on, is we're going to give you more than one equation to work with at a time. And what will end up happening is you'll be given a parameter where you'll make like a graph like this and you'll shade a section, but you'll make a second graph and you'll shade a section. And you might even make a third graph and shade a section. And by the time you're done, there's only a small parameter of answers that fit everything. And this is kind of like what a business might need to do, where they'd say, okay, well, everything here doesn't work, but everything there doesn't work, and everything here doesn't work. And by the time you're done, only the answers that fit within this small section here are valid ways of achieving your goal. Does that make sense? So take 5 minutes here, and then why don't we try at least to... Are you guys okay with this button there? Yeah. Okay. Print off the part 2 example, because it's really just 3 examples. And we'll try some of those as a group. So, but take 5 minutes first. Yeah. You guys let me know where you're at. I don't know if you've ever been in this scenario before, but let's say you want to commission someone to build something for you. In this example, I said, I want to build a table. One of the considerations you might have, though, as a person is a budget. Because you can't afford to buy a table that costs $12,000. Okay, so it's just not reasonable, right? So then you have to ask the question, okay, well, what? Guess. You might have to ask the question then, like, well, based on my budget, what can I afford? Can I afford this much or this much? Like, which model fits my budget? Does that make sense? So to start off with, we need to try to write some sort of inequality. I can guarantee you that the inequality is going to end with this. Whatever I build has to be less than or equal to 50. Does that make sense? Like, that is guaranteed to be my starting amount because money is something that limits me. The question you have to ask then is, well, what has to be less than 50? And maybe I could start off by writing this as, well, like my price has to be less than 50. Right. My overall cost has to be less than 50. Well, how does my overall cost get calculated? Well, as I read a little deeper, apparently it costs me $30 for the amount of glass I use, but it also costs me $3.50 for the price of aluminum. That better be less than 50. So I guess in theory I could make a table entirely out of glass or entirely out of aluminum. Does that make sense? The way I was envisioning this is maybe you make a table where the table is a circle, and then the area of the circle itself is kind of like the base, and then like you put some aluminum around the edge as like a circumference. So like this is of glass, and then around the edgings of it, use some aluminum to make it look fancy. Does that make sense? Well, how much glass do you need? Well, it depends on the size of the table then. If you make a table this big, I can probably afford it. But if I make a table the size of the tables you guys are working at here, it's going to cost a lot of money. Does that make sense? So, how much glass am I going to need? Well, it depends on how big the table is. What's the formula for like an area? Well, not if it's a circle though. Good, pi r squared. What we could then is say that this is 30 times pi r squared. Oops, I should do that properly. 30 times pi r squared. That's the formula for how much glass I would need. It would be 30 bucks times pi times the radius of my circle squared. Well, if the aluminum is going around the outside, does anybody know the formula for circumference of a circle? Good, pi times diameter. Sometimes it gets written like this, though. I'll just write this over here. Area is pi r squared, and circumference is pi times diameter, or it's 2 times pi r, because the diameter is twice the radius. I'd like to keep the same variable everywhere, so I'm going to make it 350 times 2 pi r. We're going to make that less than 50. And this is an equation that I can plot. Well, not x's or y's, but I can kind of change things around a little bit here. The variable I have inside the equation is like the radius. So I'm going to make the radius be x. And this over here is supposed to be like, say, my price. I might just take that 50 out temporarily. I'm just going to make it like something like this. Y equals 30 pi x squared plus 7 pi x. You guys get how I converted it to that? I lost you on that one. The 30 pi r squared just became 30 pi x squared. This was 350 times 2. So 350 times 2, I made 7 pi x. I now have an equation where really x is my radius. What is y going to be? Well, 50 is my max that I can spend. But 50 really refers to how much it's going to cost. Yeah, in a way, I now have an equation that relates my cost to my radius. As my radius increases, my cost will increase. Does that make sense? And what I'm going to need to do is make sure that this does not go above 50. So now I'm going to place where I can graph this thing. So part A, where it asks me to write a linear inequality, I guess I kind of have something that works like this. I'm just going to make the inequality go back to this one right here. Here I say it has to be less than 50, but I'm going to make it x's and y's just so that I can actually plot this thing now. So let's draw a graph. My cost, y, is equivalent to 30 times pi. Yeah, second power. X squared, pardon me. And then we need to add 7 pi x. Okay, let's talk a bit about what x and y are supposed to be. I don't think so. I think we can just type it in just like this. So before I go to my window, what is x referring to? My radius. 0 to 30. 30 meter radius table? That would be like the size of the, well over the size of the classroom. I don't know. Table, 2 meters seems excessive even. I'll adjust if I need to. And then for the other one here, for y max, y is how much cost I'm expecting to have, right? So in terms of how much cost there is, 50 probably seems like a good upper limit to set. Because, I mean, that's what it said. It couldn't go more than, right? Did you get this? Make sure that's what Jim typed in. Okay. Is everybody able to get this graph here? Okay, so I'm just gonna start a new slide for drawing our graph. I don't even think 2 is necessary because 2 was well more than I needed. But this went from 0 to 50, and from 0 to 2, and the graph looks, it's probably like half a parabola. Now I gotta start figuring out where to shade some of this stuff here. Yeah. Is it reasonable for me to pick a point way over here? Why? Well, it would make it a massive table, and would I be able to afford that particular table? No. Really, in terms of limit, $50 right here is kind of like my price limit.
Bethany Bravo,
this really refers to the radius of the table.
Bethany, please come to the
and
office.
This refers to how much money I can spend.
So that entire side is just shaded.
Yeah, it's probably best if I shade basically everything over here. Does that make sense? So now let's talk through some of the points that are left over. Right here might be a point. I'm just gonna use the, you guys ever use like the trace function? Or if I just press graph and then I just start pressing up and down, you might be able to find your cursor and just kind of mess around with the cursor. You guys ever done that before?
I don't know where it says. Oh, it's a big. What? Oh.
You should be able to see it, I think, but you just press graph and just start pressing down and over side to side. Okay, so just press graph a second time here, and then just start pressing over, and that should get it off the line. Oh, I forgot to point something out here. There's a way to make your graph actually shade on the calculator itself. I should show you this. Go to y equals. Okay, and then go over to like the little line that's like diagonal like that. Now I've shown you this toggle already. If you toggle it once, it makes the line dark. If you toggle it again, it'll do like a shade. See how it's like got a shade, like a half shade here? If I graph this thing, I can get it to shade a section of graph. The only problem I have here is that mine just shaded the wrong section. So if I go to y equals and I go toggle it so that it, you see how this is like on the top half of the line? If I press enter again, it'll toggle it on the bottom half of the line. And it should now be able to shade, and you guys might even have color on some of yours.
No.
You do, I'm guessing, right? Yeah. Not those ones, obviously. But basically I can shade this in so that this right here is the uppermost limit. Let me show you one other thing here then. You know how we made our graph go to 50? What if I just made the graph go up to 60? Okay. So I'm just going to make the graph go a little bit too high. What I could do then is I could then put a line in, a second line in at 50. So I'm just going to put a line right across there. And what I'm going to do is I'm going to shade the upper side of the line, saying that I can't afford everything up top there. Yeah. See whether you can make your graph look something like this. Where I now made it go to 60 instead, and I'm kind of like shading it like this so that everything in this sort of area right here is something that you can afford to do, basically. Does that make sense? So then anything that falls inside this little section here is a table size that you could make. Could you make a table of size 0? I guess. I mean, you're not actually getting a table technically, but I mean, does that fit your budget parameters? Could you, in theory, not buy a table? Yeah, I guess you could, right? Or as you keep going here, as this radius increases, this would be you using all of your money. Right? If you made a radius of this size right here, you'd be using every single last penny you have. And as you change your radius, as you go along this line right here, you're how do I phrase this here? You're making a table that's smaller, but it means you'll have money left over. Does that logic make sense? Yeah. Okay, so let's try an example here then, number C. If you were to buy 12 meters of aluminum, how much glass would you have to be able to buy with your remaining money? You know what, actually, I'm going to skip some of these questions here. I'm going to skip down to D. Let's say the table has to have a minimum radius of 0.5. Let's just do this one here. If your table had to have a minimum radius of 0.5, on this graph that I just drew right here, that means that 0.5 is somewhere right about here. And if I'm going to have a minimum radius of 0.5, it means I need to draw like a line straight up and down at 0.5. Your calculator can't do that. Your calculator cannot draw perfectly horizontal lines, unfortunately. So you kind of have to imagine that you have one right there. That being said, if it has to be at least 0.5, how do I shade on this side of the line here? If it has to be more than 0.5, then I want answers in this little section here. So I would shade this little bit here saying that...
Mr. Forrester, can you please call 100?
Is it fair for me to try to make a table that has no radius? Okay, I'd say no, it has to at least be bigger than this. And so this is now kind of limiting where my answers would be. Okay. One last thought on this one, and then I'm going to try the next example. The very, very last question then says label the vertices of the new solution set. Vertices would be right here, here, and here. Vertices would be the corners. And what I might ask you to do is find me where they intersect, which we actually have a tool for. Like literally, go find intersect, and you can find where these things cross. Okay, so this one's trickier because there's physically not a line there. I'll show you how to solve that in a second though. But we can find where these lines cross. They cross over here at 0.62 and 50. Okay, what does that point mean then? What does 0.62 comma 50 mean?
That's the base.
Yeah, that's the biggest you can make your table, right? If you had a radius of 0.62, that would use all of your $50 budget, and you'd have none left over. Could you use less than that? Yeah, I guess you could try to use less than that, but that seems to be the most you could use, right? If you want to try to find these vertice points right here, since you can't draw a line straight up and down, you need another trick. I would do this. Go second, calculate the value at 0.5. Okay, apparently I didn't draw 0.5 in a very logical spot. Apparently it's way further over, I guess. But at 0.5, 0.5 goes with 34.55 right about here. What does this imply right here at this point?
So it would be boxing?
That's the lowest I can build my table. Remember how I said I wanted a table that at least is a certain size? I can build a little mini table, but that's kind of pointless, right? So if the smallest I can get away with the table is at 0.5 for a radius, then it would cost me $34.55. So I'd have $15 left over. Does that make sense? If you want to find this point up here, press up. Okay, if you want to find, like this was one point right here. If you want to find the other point, just literally press the up button. And it'll take you right up top here. I think we could have known though that this was 0.5 and 50.
So how do you find the very bottom?
Oh, so go second, calculate the value when x is 0.5. Mine is not drawn very well, obviously. 0.5 is actually not right about here. It's actually further over. Yeah, like this is not to scale. Like 0.5 should have been more like right about here, I guess. It should have looked more like this, I guess.
Well, yeah, Yeah, that makes sense because our graph only goes to 2.
Yeah.
Yeah.
Okay, does this kind of make sense here? The idea being that if I give you parameters, you can figure out things like the biggest you can make your table, the lowest you can make your table, and how much money it would cost in each of these scenarios. Right? And then if I were to ask you, okay, well, what if you want the radius to be 1 meter? Well, then if the radius is 1 meter, find the value of 1 meter, and it'll cost you $116. Well off my graph. Apparently that's outside my budgetary limits. So I can't make a 1 meter table. Does that work? Okay, let's try one more example. If I finish it in the next 10 minutes, I finish. If not, then we'll do it tomorrow. Okay, so here's I don't know, maybe this is practical for some people. You're a farmer and you have $12,000. And that's all you have for your capital because that's what the bank's willing to lend you. Or maybe that's what you've made the previous year. Does that make sense? But like that's your upfront costs. And you want to plant some crops. And apparently you have choices. You could plant corn or you could plant wheat. Now, maybe you'd want to plant wheat because wheat is cheaper. At least it's cheaper for you to plant. Does that make sense? You might not want to plant wheat though because you don't get paid as much as if you do corn. I actually don't know the prices, so I'm just making them up. But does that make sense? Like you basically have the ability to plant some wheat and some corn, and the question is, which ones are you going to plant? So first I want to write an inequality. To do that, I should really label what some x's and y's are going to be. X could be how much wheat I plant, whereas y could be how much corn I plant. Does that make sense so far? Here's a practical limitation. As a farmer, I only have 80 hectares to plant. So here's one of my limitations. However much wheat I plant and however much corn I plant cannot exceed 80 because that's how big my field is. I don't have any more territory with which to plant other than the 80 that I own. Does that make sense? That's one of my limitations. But I have a second limitation. My other limitation is I have a budget. My budget better come in at under $12,000. Any thoughts as to how to fill out the rest of this particular inequality? Well, I mean, you have to plant some wheat, but wheat costs you money to plant. It costs you 100 to plant wheat. And it costs you 300 to plant corn. So now I actually have two limiting factors. I'm limited by the size of my field, and I'm limited by the amount of money I have as upfront capital. Does this make sense? Okay. So now I'm not just going to plot one equation on my graph. I'm going to plot two equations on my calculator. So to do that, though, I need to rearrange them so that I can graph them. So the first one's easy to rearrange. It's going to be y equals 80 minus x. That's what this one's going to turn into. Just subtract x to the other side. I'm going to call that y1. What about the other one? How do I rearrange this one to get y by itself? The 100x, though, it needs to get subtracted. So make it 1200 minus 100x, and then divide it all by 300. So, go graph these. One of them is 80 minus x, and the other one is bracket 12,000 minus 100x divided by 300. All right, I'd like to do this one at a time in a second here, though. So could I've shown you guys how to just turn a graph temporarily off, have I like just pressed the number of the equal sign so that it's not highlighted? I'm just going to do one graph at a time here. Before I do that, I need a window size. Any idea what I should make my windows go from? We'll definitely start at 0. What is the most I could plant for wheat? I guess, in theory, I could plant everything as wheat, I guess, right? I could just not plant corn and just say, screw it, I'm just going to plant the other one. The other possibility is I could plant corn. But again, the most I could plant for corn would probably be 80. So, now let's graph. Here's a graph that goes from 0 to 80 and 0 to 80. One axis talks about how much wheat I plant, and the other one talks about how much corn I plant. It basically just looks like this. Which side of the graph should I shade? You're right, yeah, the right side. Because hopefully logic dictates, could I plant 0 corn and 0 wheat? Sure, I guess you could. That's being kind of lazy, but you could. But way over here, could you plant, like, say, 60 of one and 70 of the other? Well, you can't physically plant 60 and 70 because your field isn't big enough to plant 60 and 70. So this side over here is the one we want to shade, because it's the side where the answers are not. So then I'll go find a way to toggle this so that it shades the top half. And hopefully it'll look like this. Does that make sense so far? Okay, that's one of my parameters. I am logically limited by the size of my field. But another logical parameter is I'm limited by budget. The bank only lended me 12 grand, or I apparently only saved that much money, right? So I might be in problems because maybe it costs too much to plant the other one. So I'm going to just turn this one temporarily off and then work on the other graph. The other graph looks like this. So drawing it, it looks like, I don't know, that. Which side of this graph should I shade? Okay, let's talk about this. Again, over here, could I plant nothing? Can I afford to plant nothing? I guess in theory. Can I afford to plant 100 of everything? I mean, one, I don't have enough room for it, right? But two, I can't afford to. My budget doesn't account for that much. So again, a point way up here is not logical because I can't afford it. Plus, I can't actually, have the space for it. So this graph right here also needs to be shaded. And what ends up happening here, do you guys see how I'm like shading over a section that used to be available? An answer up in this little section right here, although logically I have enough room in my fields for this much wheat and this much corn, I can't afford it because corn's too expensive. So what I'm hoping when we're done is if I shade, I'll now have two different lines both shaded. And your calculator looks kind of cool actually once you have this shaded. Oh, I better turn the other one back on again. Let me know if you can't get your calculator to do something like this. Yeah, we'll have to talk in a bit. Sorry. Yours doesn't work?
This is supposed to have 12,000. There we go. I'm just having fun with changing.
Okay, one last thought, then we can call it a day. If I ask you for the vertices then, let's talk about what the four vertices mean. Right here is a vertice, right at the edge of this, I don't know, it's not a parallelogram, it's like a four-sided object. What does this vertice right here mean? Right here, the guy plants only corn. Does that make sense? And really what's limiting him is the fact that he can't afford to plant anymore because his budget isn't enough to plant more. So this point right here is if he plants only corn. And let's try to find its number here. I would go second calculate the value when x is 0. And I get 80. But if I toggle it back down, it gets as low as 40. So that could be 0 with 40. So I guess in theory you could plant no wheat and only plant corn. That's a possibility.
With the following students come down to the office right now. Brody Zimmerchuk, Ryland Schubert, Liam Doyle.
Oh, so like when you do the value, when x is 0, it's going to have to choose between which line you're on.
The office right now.
So right now I'm on the Y1 line. If I press the down button, it'll take me to the other of the 2 lines. Do you see how like the lines are changing here? Okay. We might be out. Sorry. It might be in a box behind Peter in the back cupboard there, but I think we're out of that too, actually. You didn't get yours to be able to toggle up and down somebody?
It is now.
Okay. Okay. Sorry, I'm going fast here. Does it make sense then that this point right here is where he plants just wheat?
So that I can,
Okay. What about this vertex right here? What is that vertex? Well, he plants some wheat, and he plants some corn. He plants like a little bit of each, right? But what he's doing is he's maxing out his budget, and he's maxing out his field. Does that make sense? Because right here, if he plants only corn, he's not a very smart farmer because he's wasting farmland. Because he's got farmland that's not being used. Does that make sense? If he plants just wheat over here, I guess that's fine, but he's only planting one type of crop. So he's using all of his farmland, but he can actually afford to plant more. Right here is maybe the best point where he plants some corn and some wheat, but he's simultaneously using up all of his land and he's using up all of his budget. And to find that, you need to intersect. All right. Sorry, I know we're running out of time. We'll do one last example tomorrow. Thanks for bearing with me.